Hi, the topic of my project is performance of turbo-coated OFDM in AWGN channel. This project is done under the course of wireless communications and under the guidance of our professor Dr. Wu. Let's get started. First, we'll talk about the introduction. For high-speed wireless communications, orthogonal frequency division multiplexing is the most advantageous method for modulating signals. The damaging effects of multipart fading are lessened by many small narrowband channels which are obtained by dividing a wideband frequency fading channel. This is the important principle on which OFDM works. For a particular noise channel, the theoretical maximum information transfer rate of the channel is the Shannon limit or the Shannon capacity. A very important advantage is that OFDM uses IFFT and FFT operations, modulation and demodulations that can be done which are efficient enough for computations. Before 1993, a decoder with infinite complexity was used to achieve a performance near Shannon's limit. Convolutional codes was an outcome of the following. Non-schematic convolution codes were converted into cis-schematic convolution. Soft input decoding were used as an interleaver. Turbo codes perform forward error correction. In the turbo cliff region, the combination of OFDM and turbo coding and decoding can be used to attain Shannon's limit performance. Now we'll talk more about different forms of OFDM that were already previously used. The first is the single carrier FTMA system, in which the system modulates information onto either frequency or phase or amplitude. Symbols are a group of bits in digital signals in which information is stored and these undergo modulation onto the carrier. As the data rates are increased, the duration of one bit shortens. So this is the important principle which is used for SCFTMA. For frequency division multiplexing modulation system, which is actually known as FDM, it extends the concept of single carrier modulation by making use of many subcarriers within a single channel. The total data rate is divided, and one positive point is that the data needn't be divided nor do they need to be from the same source. The existing approaches till date are the convolutional codes which are being used. They do not have a fixed block length and it is rather a continuous process, and it could span an entire message rather than a group of bits. But in turbo codes, we can have a discontinuous modulation which actually helps us to reduce the power and can be used to the user's convenience. There are many applications of convolutional codes which have been used, and they are used for achieving high data transfer rate for digital video, radio and mobile communication. These are also used for satellite communications too. These are particularly implemented on Reed-Solomon codes, and prior to turbo code, such constructions were most efficient, coming closest to the Shannon limit. So this tells us the main objective of our project, to come over convolutional codes and make use of turbo codes and make a comparison on which is better. Now we'll come to turbo codes. Turbo codes actually are known as PCBC or the PCCC. PCCC are the convolutional codes that were already used, and turbo codes were used to improve its performance. Turbo codes actually make use of two blocks. One is the encoder and the other is the decoder. The turbo encoder is shown as this. The property of parallel concatenation is exploited, which is shown in this figure. The input is a sequence of binary data which is represented as X suffix I, which is the input sequence passed into the input of the encoder, which is convoluted. Then the data sequence is interleaved. And then it is sent into the matrix, which is loaded with the bits, and then it is spread out into the matrix. There are two encoders in which they take the two values which are coming out of the interleaver. Then comes the modulator, which receives the data next, and transmission is then multiplexed. This data sequence is composed of systematic code bits. We'll now have a look at turbo decoder. From the modulator, the signals go to the turbo decoder, which is in the form of a sequence of the received codes. The turbo decoder consists of two component decoders. This is mainly to decode from sequence 1 and the other to decode from sequence 2. The data sequence D is a soft estimate of the transmitted data. This data is sent from decoder 1 to the decoder 2, but it is extrinsic, so it will not have those values. For the analysis, we make use of the Viterbi algorithm, which is used for decoding the convolutional codes. This makes use of the decoding trellis, which is eventually records the state of the encoder at a set of time instants. This works on the principle of rejection. The algorithm works by rejecting the most likely path at each node by the trellis. Now what is left is a single source path which is kept behind. Now we come to the evaluation. There were few simulation parameters that were considered for this project. There are different modulation schemes available. For this purpose of the project, we use BPSK, QPSK and QAM. The turbo code rate is fixed for 1/3. And for the convenience sake, we took it as 1/2. The decoder uses a maximum A posterior, that is log map. The code generator is 111 and 101, and a pseudo-random interleaver is used. Now we'll have the algorithm for simulation. The information bits were randomly generated and turbo coder encoded with generator matrix. The binary bits were converted to complex signals by using QPSK or QAM, and serial to parallel conversion was performed. Zero padding was done. OFDM signals were generated using inverse Fourier transform, and signals were serially transmitted using parallel to serial converter. Noise was introduced for channel errors, and the receiver side reverse operations were performed to decode the sequence. The false bit were counted and DAR is plotted. This is the algorithm of simulation. Now we'll come to the performance evaluation. Power was one of the important factors that was used for consideration, so that it is used to perform well in operation under fading channel compared to a system with uncoded fading. This table shows us a comparison of the SNRs for different code generators. Now the code generator with 1 and 5/7, the SNR for BER of 10 to the minus 2 is 7.2, and for 10 to the minus 3 is 8.9 dB. And for the code generator with the interleaver of 1 and 15/13, the SNR is 6.8 dB approximately, and the SNR for BER 10 to the minus 3 is 8.3 dB. Now this table shows us the comparison of turbo coded OFDM and convolution coded over uncoded. So the main objective of this project is to compare the performance analysis of the encoded OFDM and the uncoded OFDM. So the coded is with the turbo codes and the uncoded is without any coding techniques. Now the convolutional coded, which is the primitive one, again at 10 to the minus 2 is 4.8 dB, and over minus 3 is 5.2 dB. For 16 QAM, the gain is 6.5 for 10 to the minus 2, and for 10 to the minus 3 SNR is 7.5. The QPSK, it is 11.5 for 10 to the minus 2 and 13 dB for 10 to the minus 3. So this table clearly shows that the gain has improved for turbo coded, both for QPSK and 16 QAM. But for QPSK, the gain is more as compared to 16 QAM. Now we'll come to the performance of turbo coded OFDM in noisy channel. The previously used noisy channels were Markov channel, which had a gain of 5 dB for 10 to the minus 2 SNR and 2.4 dB for 10 to the minus 3 SNR. Now, since we are doing this analysis in AWGN channel, the gain has improved drastically from 7.5 dB and to 7.8 dB. Now we'll come to the conclusions. This project mainly gives a detailed knowledge of the communication systems using OFDM. We understood that error correction codes are important and turbo codes are better than convolutional codes. We studied the architecture of the encoder and decoder of the turbo codes. We also saw the map algorithm, which uses Viterbi basics, which help in the easy decoding of convolutional codes. There were few steps that were implemented. An OFDM system was modeled, and the main motive of it was to improve the performance, as it is the main aim of all the main communication systems. Forward error correction codes are the best way to improve it, so the codes that have been used are the convolutional codes. Now we use the turbo codes. We aimed at improving the performance more. The turbo codes were introduced. They were used in uncoded OFDM systems. Lower order decoding iterations were evaluated for turbo coding systems. OFDM can be used for many applications like high speed and data applications when the BER is in the range of 10 to the minus 2 and 10 to the minus 4. The combination of good spectral efficiency, high data capacity, and its avoidance to interfere as a result of multipath effect makes it ideal for high data rate applications, which are the most important factor in the present day communication systems. The system's model developed is very quite flexible and can be easily modified or extended to study the performance of this scheme. Now we'll have a look at the different MATLAB codes that were simulated for this project. First, since this project is aimed at doing the convolution in the AWGN channel, we first wrote a code for the AWGN channel, which is as below. This is the output that we get, which is the spectral density of the thermal noise and the frequency. The BER of the OFDM channel, which have been plotted, are as below. This code does the OFDM, calculates the BER versus SNR of the OFDM channel. The simulation is like this. The bit error probability curve versus the EB by NR for OFDM. This uses BPSK, and in our project we combine both all BPSK, QPSK and QAM. For QPSK, we have this output, which clearly shows that it is similar to what that is there in BPSK, but there is no overlap. For normal BPSK that we have, we have the following output. So this mainly covers our project. Thank you to Professor Wu for his guidance and our TA for his invaluable help. Thank you.